Okay, so today's notes are going to be on pink. So we're going to start on pink page 149. Pink page 149. And we're going to start talking about significance testing or hypothesis testing. So, what we did in Unit 4 was we took information and we made some sort of claim, right? We made a confidence interval or a claim about the data. We claimed that these intervals contained the true values that we were looking for. And Unit 5, we're basically doing the opposite. We're going to be given the claim and we're going to test its validity against the data that we have found or the data that has been collected. So instead of making our own claims, we're going to be testing the claim that is given to us. It's actually great because Unit 4 and Unit 5 use a lot of the same information. So if you look at your formula packet, or I took a snippet of it at the top here, but that we have a formula packet that's at the beginning of your workbook. I believe it's pages like 3 through 5 or something like that, or 5 through 7. All of those are kind of the formulas that we've been working with up to this point. And for these particular ones, we've used these when we talked about confidence intervals for t intervals. They're also going to be used for us when we talk about t-test. So these conditions, you'll notice, are the exact same conditions that we used for a t interval, and we're also going to use them for our t-test. So that's the nice part. These formulas up here are super useful to us if we were trying to find the confidence interval or if we were trying to figure out the validity of the claim ourselves. If we wanted to compute it by hand, these formulas come in handy. Lucky for us, we don't really need to compute it by hand because our calculator is going to nicely do it for us. But there are formulas that your calculator is running and deriving for us that we're just lucky enough that it's going to do it instead of having us do it by hand every single time. It just makes it more efficient as we're running all of those tests. So remember, a lot of testing these claims is going to be creating a null and alternative hypothesis, and then from there, testing which one of those is going to end up being most valid for us in this situation. So remember, for our null hypothesis, we always use the equal sign when we're writing it. It can symbolize these two equalities, but we always write it as an equal sign. And then our alternative hypothesis, we're going to use one of these three symbols. So not equals to, less than, or greater than. And that kind of goes back to our talk from yesterday. So what we're doing in this case is we're going to get a claim and some information about a study that's been done. And we're going to test the claim against this study. And what's going to come out is a test statistic, and it's a value that helps us make the decision about the null hypothesis. So it's converting all of these assumptions into a value to tell us if our null hypothesis is true or not. What we're going to test it against is called a significance level. So a significance level is just, or we can also call it a critical value, is kind of the cutoff point if we're going to accept or reject the claim. So we most commonly use these three critical values: 0.1, 0.05, or 0.01. And I think it'll make a little bit more sense once we look at an example. But what we're going to do is we're going to end up running a t-test. We'll get a value, and then we'll compare it to whichever one of these three values we're asked to compare it to. So to run it on our calculator, if we're running a t-test, and again, the rules or the idea of running a t-test is very similar to when we ran our t-intervals. So this is when we're given a mean and a standard deviation, right? We're going to run our t-test, a mean and standard deviation, or a table of values. Right? Remember, we can find that information from a table of values as well. So when we're given this, we can run a t-test. We hit stat, go over to test, and then we're going to pick the t-test, which I believe is number 2, is our t-test. The things we need or our claimed value. So this value comes from whatever claim we're making. And then we ran some sort of, or somebody, I'm not going to say we, but there was a study being done or an experiment being done where data was collected. So then we have this data from a study that we're going to use this data to test it against the initial claim. So I think it is the easiest if we look at an example. I think just kind of seeing how all of this goes kind of helps us when we're testing these things. What I want you to be aware of is that all of your t-tests are set up exactly the same. So we're going to have the same format. And if you go to page 140, it's like 143 or 147 in your workbook. Let's see. Oh, totally off. If you go to the white page 203, this is what's on there. All of our hypothesis testing in Unit 5 is set up the exact same way. So we're going to have a problem. We have to figure out what variables we know, identify the appropriate test, check for our conditions. Yeah, this is all kind of similar to our confidence interval testing. Then we're going to identify our claim, write our null and alternative hypothesis, and then we'll check those claims, right? We'll check those claims in our test statistic, and then we're either going to reject our null hypothesis or fail to reject our null hypothesis, which will then allow us to write a conclusion at the end. So whatever we decide, right, whatever our p-value comes back, we're going to get some sort of p-value, which is going to tell us to either fail to reject or to reject, and then we'll write a conclusion about that claim that we talked about up here, and then identify the claim. If your p-value, and I was told this when I was in high school and I still remember it, if your p-value is low, you reject the HO, which is your null hypothesis. I know it's not very statistically sound, but people tend to keep that in mind. So when your p is low, reject the HO. If it's not low, if your p-value is greater than your critical value, then you failed to reject. And really what that's telling us, and if we think about, we can turn our page over to 150, right? The p-value or the probability value is the probability of getting a value that is at least as extreme as the one representing the sample data. So really getting our p-value means that we're getting a value that's a super low p-value means it's really outside of the scope of what you would normally get, right? If we think about our normal curve, all of that stuff in the middle is kind of what we would assume is the norm, right? It's the majority. So if we get a p-value that's way outside of that, either on either end, we're rejecting our null hypothesis because that's an extreme it's an extreme to assume that the null hypothesis is true. It's an outlier, or it's something that would not happen that often. So we're going to, the nice part is our calculator is going to produce the p-value for us. And then all we do is compare it to that critical value, which is separating the region between kind of our norm or the green of our failed to reject area. This is kind of the stuff means it typically happens, and then that outlier or the stuff on the outside is the extreme cases that have a low probability, a low p-value. Okay, so like I said, I think it will make more sense when we look at some examples. So what I'm going to have you do is turn to page 151. If you turn to pink page 151, we're going to look at an example of what this t-test would look like, what running a hypothesis test looks like. So your company is selling clothes. We're going to look at this first one. Your company sells clothing on the internet. To design the clothing, you collect data on the physical characteristics of your different types of customers. According to a report published by CBS News, the average male is now 195 pounds and 5'10" inches tall. 5 feet 10 inches tall. Your company wants to confirm this before designing your clothing line. You take a random sample of 34 men and find their mean weight to be 197.9 pounds with a standard deviation of 5.9. So in this case, right, the initial value, that initial mean that we're testing against is this 195.8, excuse me. Right? This is our published announcement, that our mu value, we call it mu naught, that initial value is 195.8. So then we want to test the validity of that against a sample that we collect. So we took a sample of 34 men, so N would be 34, and we found their mean weight to be 197 and their standard deviation to be 5.9. So we're taking our sample and we're testing it against this claim that was made. Because we're doing a mean and standard deviation, this is going to be a t-test. Remember, your t-interval conditions are the same as your t-test conditions, so that's nice. We have 3 conditions to check. Is it a simple random sample? Is our N value greater than or equal to 30? And then is our population size independent of the entire population? So it says that we took a random sample, so we can say that worked. Our N value was 34, so since that's greater than or equal to 30, we feel good about that. And then our N value, right, if we take our N value and we add a 0, it is reasonable to assume there are more than 340 American men that we could have asked to be a part of this study. Okay, so this number 2 part is just asking us to kind of review Unit 4 again and make our confidence interval. There's good practice for us just to kind of see how these two correlate. So if we make a 95% confidence interval, we already have all of our information here. So we're going to do a t-interval first, and we'll just compare what we get at the end. So our x value is 197.9, 5.9, 34, and if I want a 95% confidence interval. So it says that I have 195.84 and 199.96. So, based on the confidence interval, does this support that my average age is 100, or my average weight is 195.8? I would say no, because 195.8 is not in this confidence interval, right? We are 95% confident that the actual mean lies in this interval. 195.8 is not in this interval. So So we could do this if we wanted to test the validity of our claims. We could run a confidence interval and see if that claim falls within our confidence interval. But the t-test is really another method, or I don't know if I would say a more accurate method, a different method to do the same thing, to test that claim. So what I'm going to do, and this is where it kind of gets different for our t-test, is this bottom section is what we're going to have to do, right? This top stuff looked pretty familiar from our t-interval, and now this is how we run a t-test. So first we need to identify the claim. We just write out our claim in words. So that would be, right, the report that was published that the average male is now 195.8 pounds. So then if I want to write my null and alternative, right, we're saying that the average weight is 195.8. So that is equality, right? It is 195.8. So this is our claim. Which means the alternative would be that it is not 195.8. Right? The opposite of equals is not equals. So we wrote our null and alternative, and now I'm going to run my test to see the values that I get. So with my calculator, I'm going to hit stat, go over to test, and then I'm doing number 2, which is the t-test. So then I'm going to input my own data, and look, it's already got some of it saved, right? My mu is 195.8, my mean is 179.9, standard deviation 5.9, and n value 34. Because we typed a lot of this into the hypothesis testing, or the t-interval, it actually carried the values over for us, which is pretty nice. So then the last thing we need to select is our alternative hypothesis. Which of these values, or which of these inequalities did we use? We ended up using not equals, so we're going to select that here, and then we're going to run down and hit calculate. So in my t-test, I type in all of these known values that I wrote for myself up here, and then this bottom part is just whatever symbol you used for the alternative hypothesis is the one you want to select down here. So then I hit calculate. My test statistic, or my t-value, is 2.075. My critical value, let's see, does it ask me to use a certain critical value? It does not. So if it doesn't ask me, I usually just use 0.05 as my critical value. That's the one in the middle. It kind of makes the most sense. And I get a p-value, right? Our p-value is 0.0458, or 0.046. So since my p is lower than this, since my p is low, I reject the HO, or the null hypothesis. So that means I am rejecting this, which also means I'm rejecting my claim. Rejecting the null hypothesis does not always mean you will reject the claim. It does sometimes mean that, but not always. So then you're going to write a conclusion about what just happened, and it relate it to the claim. So in our case, we rejected the claim. So what I would write is there is sufficient evidence You could write there's not sufficient evidence to support the claim, or there's sufficient evidence to reject the claim. And then I literally just write out the claim after that. The claim that the average American, or the average male, weighs 195.8 pounds. And then I'm done. I ran my t-test. I found out, right? And we had kind of said in our interval that it's probably not the right average rate. And we confirmed it here in our t-test that it is not the average weight. Okay, so what I would like you to do now is if you turn to page 152, and you don't have to, but if you feel comfortable trying the one on page 152, see how far you can get on your own before watching the video. So pause the video, see how much of this information you can fill out based off of that last example on your own before trying it. If you don't feel comfortable with that, I'm going to go over it right now in the video, but it's always a good idea to kind of figure out what you know and what you don't. So if you want, pause the video, try to fill out as much as you can, and then watch the video to kind of fill in the blanks for you. All right, so number 4, the survey of study habits and attitudes is a psychological test that measures the motivation, attitude towards school, and study habits of students. Scores range from 0 to 200, with 200 being the highest level of motivation. The mean score of a U.S. college student is about 115, and the standard deviation is 30. A teacher who suspects that older students have better attitudes towards school gives the SSHA to 40 students who are at least 38 years of age. Their mean is 135.2. Okay, so we are testing, right? The claim that is being made before anyone does a study, the claim that is being made is that the mean score of students is 115. Is about 115. So 115 is going to be that value that we use, right? That mean that we're going to use over here. That's our initial mean that we're testing against. Now, the teacher suspects that older students have better attitudes towards school. So she's claiming that it's going to be higher, right? We're going to test the claim that it's higher than 115. But 115 is that initial value that we're going to test against. Our sample, right, she asked 40 students. Their mean was 135.2, and because we don't get a standard deviation, we're going to assume it's the same standard deviation as the first initial study. So again, because we're given a mean and standard deviation, just like we would run a t-interval with that information, we're going to run a t-test. We'll check those same conditions we would check in in a normal t-interval. Is it a simple random sample? Is our n value greater than or equal to 30? And is our n value a reasonable size? So we're going to assume it's a simple random sample. Our n value is 40, which is greater than or equal to 30, so we can check that off. And then it's safe to assume that it is reasonable to assume that there are more than 400 students that we could have asked to be a part of this study. So we know that initial value is 115. That initial scoring is 115. But we want to test the claim, older students have better attitudes towards school. So our claim is older students have better attitudes towards school. So our null hypothesis is always equality. But our claim is that older students have better attitudes, so that means that they would score higher than 115. So our alternative hypothesis is going to be our claim. We're claiming that they score higher. Okay, so now that we have this information, we can go ahead and run our t-test. So again, I go on my calculator, I hit stats, go over to test, and I'm going to run a t-test. So my statistics here, I'm testing against the initial value of 115. My mean of my sample was 135.2 with a standard deviation of 30 and an n value of 40. My alternative hypothesis is that it's greater than, oops, I messed that up, test, t-test. My alternative hypothesis is that it's greater than, so I need to highlight and select greater than before I hit calculate, right? Where our alternative is that mu is greater than 15. So then our t value is 4.259. It doesn't give us a critical value, so again, I'll use 0.05, and I get that my p-value is 6.27 e to the negative 5. So if you remember anything from scientific notation, p is 6.27 e to the negative 5. That means this decimal is going to move 5 places to the left. So really this is 0.0000627. So this p-value is definitely lower than this critical value. So when the p-value is low, we reject the null hypothesis, which means we reject this. That was not our claim, right? We did not reject our claim in this case. We actually are supporting our claim since we rejected that null hypothesis. So we're going to say there is significant evidence to support the claim that older students have better attitudes towards school. So is the teacher correct? Yes, I think that her claim is correct. Right? I write all of my conclusions pretty much identical. It's either there is significant evidence or there is not significant evidence to support the claim, and then I literally, whatever I wrote up here, I rewrite down here. We want to write our conclusion to be a full sentence that encompasses the entire thing. We don't want to just write yes or no or reject the null or whatever. We want this to be the summary of the entire problem, so that if someone didn't read the whole study or whatever, they could still understand what we're talking about in our conclusion. Okay, so hopefully we feel okay. We're going to do, again, a lot of practice with t-tests, but there is more than just a t-test that we need to consider. So if we look here, yes, when we're talking about our mean and average, with one population, we run a t-test. That's exactly what we just did. Those are the two examples that we did. If you look on the right, sometimes we're given two populations, which means we're running a different test. Same idea, same conditions. It's a different function on your calculator if you're running a two-sample t-test. And then there's a third one that's a little bit outside of what we've previously seen. But it's actually if we have paired data. So that means that we're testing a before and after. So like one person, a before and after against themselves. So instead of having two sets of independent data, we're actually looking at someone's data against themselves. So if you look at pink page 150, this is exactly what we were just looking at in that chart. So we learned how to do our t-tests with one population. So now we're just going to look at some examples of if we have two populations that are independent, we run a two-sample t-test. If we have paired data, like I was saying, a before and after situation, we're still going to run a t-test based on their differences. And we'll look at an example of both of those, and I think that they'll make a little bit more sense once we look at an example. But these are kind of the three different options of a t-test that we could do. So let's go ahead and look at an example of a t-test on the difference. So if you go ahead and turn to pink page 154, we're going to look at this two-sample but dependent data. And what it means is we're looking at one population and we're studying their before and after of each situation. So again, pink page 154, this is our t-test on one sample difference. It's run very similarly. It's just the data that we're comparing is against itself rather than against a claim. So number 6 says a test of abstract reasoning given to a random sample of students before and after they completed a formal logic course. The results are given below. An outside company claims that the logic course does not make a difference in their score. Construct a 95% confidence interval for the mean difference between the before and after scores. Assume the populations are paired of paired differences is normally distributed. So because we're looking at the differences, right? We're only looking at one population. Though we have all this data, we're really only going to use this data to run our t-test. Right, because we're comparing the people's before to their after. So we're looking at one set of data. Because we're given it in a table, that means our calculator can find the mean and standard deviation for us. So we're going to run a t-test because it's based off of mean and standard deviation. Now, there's 2 ways that we can do this. If you really wanted to find out your mean and standard deviation before you got started with your t-test, your calculator can do that for you. Remember, if I go to stats, and we need to do this anyway, we have to type it into a list. But if I go stats, edit, and I type all of this into list 1, which to run our t-test, we'll need it in list 1 anyway, so it's worth doing. 11, 10, -4, -2, 1, 7, 2. So if I go stat, edit, I'm going to type it all into list 1. Now, if I want to know my mean and standard deviation before I get started, I can hit stat, go over to calc, and hit that 1 var stats thing. Then if I hit calculate, it tells me that my mean is 3.7. My standard deviation we use in this case is our 4.95 or 45. And then our n value is 10. We really don't need to do this step, but if it makes you feel more comfortable, that's totally fine. Now, our conditions that we check are the same normal conditions for our t-test. So we have a simple random sample. We want to know if our n value is greater than or equal to 30. In this case, it is not, right? Our n value is 10. However, it does say that it's normally distributed. So because it's normally distributed, we can let that n value be low go away. We're not concerned because it's normally distributed. And then our n value is less than 0.1 of the population. It's safe to assume that there are more than 100 students that we could have picked for this test. So again, a lot of the conditions are the same as a normal t-test. We're just comparing data in this case. So when we identify our claim, right, the company claims the logic course does not make a difference in their score. So that would, right, there is no difference. The logic course. So that would mean, right, that difference, this value that we're finding here, that mu value would be 0. That's our claim, that if we took the difference, that the mean value is 0. So then our alternative hypothesis is that it does not equal 0. Because that's the opposite of our equality. And so now we're going to run our test statistic to see if this is true. So this is where typing this into the list comes in handy. While we can use these values, if we go stat over to test and hit t-test, we can actually tell it to pick the data out of our calculator. So instead of doing this part, doing that one var stats to get this information, we didn't really need to do that. We'll just tell the calculator, take the data out of list 1. My mu that I'm testing against is 0. There's really nothing to worry about frequency-wise. My alternative hypothesis is that it's not equal, and then I'm ready to calculate. So when we're given a list, instead of typing in our own stats, we can tell the calculator to pull the data from list 1. So then if I hit calculate, I get a t-value of 2.366. I'm going to test it against a 0.05. Because we were doing a 95% confidence interval, that's the same as a critical value of 0.05 actually, if you think about the other 5%. And then P I got was 0.042. See how these values match up with the initial values. Sorry, that glare. These values match up with the values our one var stats told us. It's because it's calculating the same thing. So like I said, you don't really need to do the one var stats, but if it makes you feel more comfortable, more power to you, it's going to give you the same values at the end. So because my p-value is lower than my critical value, I reject my null hypothesis, which means I reject the claim here. Right, I'm rejecting the claim. So I would say there is not sufficient evidence to support the claim that the logic course does not make a difference in their scores. Okay, so that's our t-test when we have that one sample difference. Generally the same idea. Yeah, generally the same idea because we're just running a t-test, but we're using a little bit of the different values, right? We're looking at that difference there when we're computing the t-test. So it is a little bit different. So let's go ahead and talk about our two-sample t-test. Our two-sample t-test is, and we actually have two samples that we're comparing against one another. It runs, again, essentially the same, except for the fact that you have two sets of data that you're comparing to each other. So if you turn your notes over to 153, just flip that page over, this is going to be our two-sample t-test, because as you can see, I have two separate samples that I'm comparing against each other. So it says 2 machines filled 32-ounce cartons of cereal. The quality control manager claims the cartons filled by machine 1 have more cereal than those filled by machine 2. Yeah, claims. It says right here, that's going to tell you your claim. Samples from each line were taken and the results following were obtained. So we're given the sample size, the mean, and the standard deviation for both of these. At a 2% significance level, so that means, and if I wanted to go down here and write it, I could write 0.02 right here. That's what they wanted me to use as significant level. Not a common one, but we can still run it. Test the claim that the population mean for machine 1 is larger than the population mean for machine 2. The populations are known to be normally distributed. So we're going to run a two-sample t-test because I have two samples to work with. I didn't ask for the variables because they're all right here, right? This is my n value, this is my x value, my means, and this is my standard deviation. So I'll make machine 1 my mu 1 and machine 2 my mu 2. And those are all the values that we're going to need to run our test. So when we do our conditions, we have to check the conditions for both of them. So is it a simple random sample? We're going to assume with this, when they're running samples on this, that they are simple random samples. We're going to check if our n values are greater than or equal to 30. So this one is 25. This one's 36. So this one's okay. This one's not. However, it says the populations are known to be normally distributed. So that normally distributed is going to make it okay that our n value is lower. And then if we talk about, right, it would be reasonable to assume that they could take 250 or 360 samples from these machines. All right, so we're testing the claim that the population, and you could write this one or this one. I don't really care if they're basically the same thing. But cartons filled by machine 1 have more cereal than those filled by machine 2. If you want to write that the claim, right, the population mean for machine 1 is larger than the population for machine 2, totally fine because it's essentially the same thing. So we're testing our mu1 versus our mu2. So if cartons filled by machine 1, right, our null hypothesis is always that it's equal, which is not our claim, right? Our claim is that mu1 produces more than mu2. So since our null was not our claim, we make the alternative hypothesis our claim. All right, so now it's time to test this. So the only difference here is when we go stats over to test, I pick my 2-sample t-test rather than just a normal t-test. And it's going to ask for the same things, right? We have stats, so we're going to type those in. And we're just going to type it in for our mu1 and our mu2. So for our first set, our mean was 31.8, standard deviation 2.2, n value of 25. For our mu2, our mean was 30.9. Oops, I just got all mixed up. Okay, 31, make sure none of this changed. Okay, our standard deviation was 1.98, and our n value was 36. Our hypothesis is, our alternative hypothesis is that mu1 is greater than mu2. This pooled, you were always going to leave as no. I don't actually know entirely what happens, but it does change all of your values. So leave it at no. And then we calculate. So our t value is 1.64 or 36. And our p value is 0.054. All right, so our p-value is actually greater than our critical value. So since this is higher than this, we are going to fail to reject the null hypothesis. That means we're going to keep this. We are not keeping with our claim then, right? Our claim was that they're different. We're saying that they're the same. So we don't have enough evidence to support our claim because we're not going with our claim this time. We're going with that null hypothesis. So I would write, there is not sufficient evidence to support the claim that machine 1, can't spell machine, machine 1 makes more cereal than machine 2. Or filled more than machine 2. So then my recommendation to the manager, right, if they're actually filling, if we're saying they are filling roughly equally, would be don't worry about it. The machines are doing fine, right? Your quality control, it seems like everything is going fine. Okay. And then I don't know what this is. This is not, I don't know how this made it on the page, so we'll ignore that. So that is our 2 sample t-test. So just running 2 sets of samples against each other and comparing the values. All right, so now you have some in-class practice, which is honestly, this is all our hypothesis testing is running these tests over and over and over again. So just getting practice, writing all of this information down. Like I said at the beginning, the format for all of your hypothesis testing is going to look exactly the same as this. So just getting used to the format and filling it in is super important. So I believe it's white pages 205 through 207 has some practice problems for you to look at.